Today, let's talk about information content and entropy, which are two fundamental concepts, first of all, in information theory, but also in computer science. So the definition of information content is that it denotes the amount of surprise or uncertainty of an event slash outcome. So event, outcome, as well as surprise and uncertainty are analogous terms. So this is the definition, but let's get some intuition on this. And we're going to use a diagram from 3 Blue 1 Brown videos, one of his videos, which has a very good explanation of what this means. So let's say that an event which cuts the space of possibilities by half has 1 bit of information. So this information content, we represent it in bits. And this is the case where we have a possibility space in blue and it's split in half, meaning that the information from this event is 1 bit. And you can think of this as a coin toss. If you have a uniform coin, which can give you either head or tails, the event happening will give you 1 bit of information, meaning that it will either be a head or a tail. And you can actually, extrapolate this example to n bits if you have n coins. So if you have 2 coins, then flipping them both at the same time and assuming that they're independent will give you 2 bits of information once that event occurs, which means that it will cut the probability space by 2 to the power of 2, which is 4. So whereas we had heads, tails, tails, head, I guess in this case we're considering, heads, tails, tails, heads, tails, tails, and heads, heads. We're considering that tails, heads, and heads, tails are different because they're different coins. Then we are splitting the probability space into 4. So this is a really intuitive way to think of information. And one thing that we didn't look at is if you come in the other direction and you have a coin with 2 heads, then flipping that coin will not change the space of possibility because the entire space of possibilities is just head, and it gives you no new information. So you would say that the event occurring gives you 0 bits of information. Nothing new has occurred because before the event occurred, we knew it was going to be heads since it was just 2 heads, and after it did not change it. So from this framing of the definition of information content, we can also have the corollary that a rare event conveys more information. So in this example, we have 5 bits of information for a 5-headed coin toss because that is a rare event to get 5 coins in a specific orientation. So this is one thing. And then obviously in the contrary, a common event with the most common event being probability 1 will give you 0 bits of information. So now I want to derive the formula for I, since we can see here that it is covered. So let's come to this this graphic here. So what is the first term on the left here saying? It's saying that for a given amount of bits, 1/2 to the power of those bits gives us the probability of the event occurring. And if we come here, then, for example, when we had a probability of 50%, meaning heads or tails, then it was 1/2 to the power of 1, giving us p equals to 1/2. Okay, and now if we take this and then just invert both terms, which is to say make everything to the power of -1, then we will get 2 to the power of the number of bits, or the information content, is equal to the inverse probability. And then this is equal to the logarithm of 2 being equal to I over 1 over p is equal to I. If you just take the log of both sides, log base 2, then you'll get this equation. And then the most common instantiation of information content is simply the following. So we have the information of x is equal to log base 2 of the negative of the probability of that event occurring. And we arrive at this formula simply by taking the negative of this side and then inverting the denominator to get just p. So I hope that this gives you an intuition on information content. Once again, it denotes the amount of surprise. And if you have a double-headed coin, for example, there's no surprise. So you can just kind of think of this as the base case where you have zero information because there's zero surprise. Okay, so now we can talk about entropy, which is a related term. In fact, it is the expected value or the weighted sum of the information content. So that doesn't really make any sense, but let's first look together at the definition of entropy, which is the average surprise. Once again, surprise and uncertainty are interchangeable. And here, the two interchangeable terms are a random variable or a probability distribution. These are the exact same thing. So it's the average surprise of a random variable / probability distribution. What does this mean? Well, let's first introduce the formula so I can tell you why it is in fact the expected value of the information content. This is because the information content term is here. So we have how many bits of information as a result of this term being evaluated. And then we will simply look at all the different probabilities occurring for the different events in our probability distribution and then sum over those events. So this is literally the definition of a expected value. So E of x, which I think is the standard notation for expected value, is simply sigma of P of x times x. And since we are doing, in this case, I said it's the expected value of the information, this is just the sum of P of x times the probability, that the probability of P of x is P of x times by the information, which is this term here. So there you can see why this is the expected value of the information, but this doesn't actually explain anything about entropy. So now let's get into that. I would like to first kind of talk about the min and max situations. So just as the information is 0 when the probability is 1, but if the probability is really low, meaning the surprise is high, then the information content is also high. So the analogous term for this is that entropy is maximized when all possible outcomes are equally likely, and it's minimized when there's only one possible outcome. So I want to take this formula and use it for a uniform coin and see what happens. So in the case of a uniform coin, we have two events with both having probability 1/2. So the term would be 1/2, which is the P of x, times negative log base 2 of 1/2. So log base 2 of 1/2 is -1, since 2 to the power of -1 is 1/2, and then -1 times -1 is 1. So we have 1/2 times 1, and then it's the same term since they're identical. It's a uniform distribution. We have 1/2 times 1, meaning that the entropy for a uniform coin is 1. Okay? So this is the maximum possible entropy that you can get for a binary event, because you can't have more than two choices. So one bit of information means it's either one or the other. That means it can be encoded by one bit, right? 0 or 1, heads or tails. But then if we have a coin which is not uniform, and in fact it's always head, then there is 0 entropy since the outcome is always heads. And if we calculate our same sum here, we will get 1, which is the probability of heads, times the negative log base 2 of the probability, which is also 1. And so 2 to the power of what equals 1? Well, 2 to the power of 0 equals 1. Okay? And then it's also the negative sign here, it's just 0. So everything just devolves to 0 in this term. And then if we calculate the tails term, well, it's 0 probability. So P of x is 0 for tails. And then we have multiply this by the negative log base 2 of P of x, P of tails, which is 0. So the log of 0 is negative. The negative log of 0 is negative infinity. If you recall, I would just say look at the graph of negative log of x, and you'll see that as x approaches 0, then the term approaches negative infinity. Okay, so we have 0 times negative infinity, and this is just 0. So the entire term is 0, and this means we have 0 entropy since we already know the outcome beforehand. Now let me give you some examples from machine learning. So entropy is used to measure the impurity or disorder of a set of data points. And we just do this by applying the probability of each data point in this entropy sum. And this is particularly useful, for instance, with decision trees, which want to determine the best attribute for splitting data. So you want to split the data in a decision tree on the highest entropy data point so that you can reduce entropy. And once again, we can consider information entropy as the average information conveyed by an event. I keep on going back to the example of a coin because a uniform coin on average conveys 1 bit of entropy. It's just the average information which gives us entropy, and that's 1, because if we have a uniform coin, then it will either be 0 or 1. So this is the basis of both information content, such information, and entropy for information theory. I think these are really cool concepts to learn, and I would recommend you to go into the Wikipedia page for information entropy if you would like to learn more about this. It's really cool too because it's really the field developed by Claude Shannon, who was the father of information therapy, and of course the person that Claude is named after. So I hope this video made some sense. I always like to think of things in examples, so that's what I did here. And if you have any questions, then be sure to comment them below. See ya.